Continuing talking about volumes of solids of revolution, we're not going to look at the disk method this time, but rather the shell method. Using this method, we're going to look at looking at volumes in a much different way. Instead of dividing it up into different slices, we are going to look at shells of the same shape in smaller and smaller form. The two ways I like to think about this is using the Russian nesting dolls. If you want to find the volume of the biggest Russian nesting doll filled in, you can instead look at the surface area of each of the individual components all the way down the line, and this would give you an approximation for the actual volume of the whole shape. Another way to think about this is if you want to find the volume of a cylinder, you could look at a bunch of little cylinders in between and find the volume of all of those. And I think looking at cookie cutters is a nice way of thinking about this, as they are stacked within each other and give you that idea. So let's look at an example where this is going to work. I'll go through it in a lot of detail, this first one. Find the volume of the solid of revolution created by revolving the area bounded by y equals x minus 1 times x minus 3 squared and the x-axis around the y-axis. So first, let's sketch this function. A nice way to sketch this function is that we know it has an x-intercept of 1 and an x-intercept of 3 and an x-intercept of 3 from the x minus 1, x minus 3 terms. Since the x minus 1 has a multiplicity that is odd, the function is going to go through that point, and since the multiplicity in x minus 3 is even, it's going to touch off that x-intercept, and that's going to give us a polynomial that looks like this. Crossing the 1, bouncing off the 3, and then going out in that direction. There's a lot of different ways that you could graph this function. This is just one of those. The area that we're looking for is bounded between that function and the x-axis, represented by this area right here. And we're going to be finding that area. We're going to take this area and we are going to revolve it around the y-axis. Let's draw a picture of what this solid is going to look like. So we're going to have our function here. We're going to revolve around the y-axis, so we're going to reflect that over the y-axis. And we have this done in a circular kind of manner. You can draw some arcs of circles there. To me, this looks like a bundt cake pan. Has a hole in the middle and a rounded thing all the way around. We're trying to find the volume of this shape, and instead of finding slices like discs or washers, we're going to do this using cylinders and shells of cylinders. And this is how one of those cylinders is going to look. So we're going to still use a little slice, a little rectangle. That's going to be important. This time we're going to draw an identical copy on the other side. And this is going to represent the edges of a cylinder here. So let's just take the cylinder. Let's look at it real quick. This is not a filled-in cylinder. This is a hollow cylinder. Just the shell of one. And maybe the best way to think about this is that if we actually just cut this cylinder at one point and we unravel it, this is exactly a long rectangle with a little thickness attached to it. Where this is the point where we cut, The thickness is the same dx that we've been dealing with before in the original picture. It's the width of that little rectangle. The height of that rectangle, h, is going to be the height of that rectangle in the original picture. And the length of the rectangle is going to be the circumference of the circle, 2 pi r. So what we're going to try to be doing is we're going to find the area, the volume of the shell, which is going to be 2 pi r times h times dx, the volume of that little box. So let's look at this again. We're going to go to the next page. We're going to redraw our shape here. And we're looking at one shell of a cylinder. And the shell of that cylinder is associated with some x value. We're just going to call this just x right now. Drawing the rest of the shell. We have that the height of this shell, h, is going to be exactly whatever that function value is, or in this case, x minus 1 times x minus 3 squared. The radius of the circle is going to be given exactly by whatever that x value is. So we could say that the volume of a shell is going to be, I should say, a shell at some x value is going to be 2 pi r h dx. We got that from the last page. And this is going to give us 2 pi. R is going to be x. H is the function, x minus 1 times x minus 3 squared, and then times dx. Now we are going to have a shell for every x value in between 1 and 3. Looking at our original picture here, we have our little area. We're going to have a shell associated with every single x value in between there. And that's going to give us our idea of this little cookie cutter kind of shape where we have these shells stacked into one each other, and that's going to give us the volume of the entire region, the entire solid. So the volume total is going to be the integral from 1 to 3. We're going to have a shell for every x value in between 1 and 3, where the volume of each of those shells is going to be 2 pi x times x minus 1 times x minus 3 squared dx. And we'll leave that as our answer right now. We could find that it's a fairly straightforward integral as long as we multiply all those terms together. Factor out the 2 pi out in front. One thing to watch out for in this problem is that when you're doing the shell method and you're going around the y-axis, it's important to know that everything's going to be in terms of x. This is true because of how the cylinder is set up, that it depend on each x value where that cylinder comes from, as opposed to the disk method which when you went around the y-axis, everything was in terms of y. That's because it was a different shape that we were bringing in. And we'll see in the next example, we'll do both methods to see the difference. One more thing about this example, though. If you did try to use the disk method, let's draw a little picture of this real quick. Since we're going around the y-axis, it's important that we would use a washer at some y value. The problem is that the big radius and the small radius associated with this problem, so R and R, big R and little r, are both associated with the x minus 1, x minus 3 squared. And the issue is y equals x minus 1 times x minus 3 squared is not a function in terms of y. So you cannot write this as y, or sorry, not y, but x equals some function in terms of y. And that makes it an issue with doing the disk method. There is a way that you could get around that, but it's a much more difficult process as opposed to doing the shell method, which was quick and easy. Let's see this done in one more example. Find the volume of the solid revolution created by revolving the area bounded by y equals cubed root of x equals 8, and the x-axis around the x-axis using disks and washers. So we're going to do this in the 7.2 way, and then we'll do it in the new way right after this. So first, let's draw the functions. We have the line x equals 8, and we have the cubed root of x, which we'll just write like that for the moment, equals y. And since it's going to be bounded by the x-axis as well, our area is this area right here, and we are revolving around the x-axis. So our shape that we're going to have here is going to be given by this thing right here. It looks like a filled-in bowl. Nice shape to look at. And when we're going to slice of this, we are going to get exactly a disc. The thickness of that disc, which is associated with a rectangle like that, is dx. And the volume here of a disc at x is going to be pi r squared times dx. And in this case, the r is the cubed root of x squared dx. So this will give us the integral volume total. It's going to be the integral from 0 to 8. We're going to have a slice for every x value in between 0 and 8 of pi cubed root of x squared dx. That's using the disc and washer method. We can also do this using the shell method, and we'll see that right now. So same problem, except this time we're going to use shells instead. So same picture. Here's our x equals 8. Here's our cubed root of x. When we think about reflecting this, taking this area, reflecting it over the x-axis, we're no longer going to look at discs and washers, we're going to look at shells of cylinders, and that's going to be, given a little horizontal rectangle, we can draw its reflected copy over here. We're going to have something that looks like this. Right? And everything is going to be in terms of y here. And that's because we are going to have a shell for every y value from 0 all the way up to, in this case, this is going to be 2, where 2 is the cubed root of 8, given that intersection point, right? So if everything's in terms of y, we're not going to look at cubed root of x, we're going to look at x equals y cubed instead. And when we're looking at some generic shell at some y value, we need to look at that shell a little bit closer. We need to find its radius and its height. So the volume here total is going to be the integral from 0 to 2 of 2 pi r h d y. We just need to figure out what is r and what is h. That'll give us our answer. So r is the easy one to find here. R is just going to be the distance from the origin out to our rectangle, and that's going to be exactly the value of y for every one that we have. So r is y here, just as r was x in the previous problem. And h is going to be the length of that rectangle. And that rectangle we can find by doing the right function minus the left function, which will give us the x equals 8 minus the x equals y cubed, or we could write that as just 8 minus y cubed. For every y value from 0 to 2, it's going to give us a different height. At y equals 0, it should give us a height of 8. At y equals 2, it should give us a height of 0, or a length of 0, I should say, the height of the cylinder. And at anything in between, it's going to be 8 minus y cubed. So plugging this all in, we have the integral from 0 to 2 pi r is y, h is 8 minus y cubed, dy. Both of these answers that we got in the last two problems are the same. It's just two different ways of going about the same problem. In some problems, you're only able to use the disk method or only able to use the shell method. It kind of depends on if you can rewrite your function in terms of the other variable. In our first example, we were not able to do it in terms of disks and washers, but we were able to do it in terms of shells. And it's important to know both of the processes. And although they are similar, the shapes that we're dealing with are wildly different.